Tēnā koutou katoa. Thank you all for attending today, and thank you for your patience while we're going through our little setup situation there. Anya's working feverishly to get the presentation right, but as it happens, we were going to start with Yale anyway. Right, welcome to our session on really decarbonising heat and renewable thermal energy. The genesis of this particular session comes from our conference. We had a superb conference in Rotorua, the home of geothermal activity, in June, and we had such good feedback about Yale and Anya's sessions that we thought we'd put them on as a webinar. So thank you, Yale, thank you, Anya, for volunteering a second time to come along and help promote the message of what can be done. So today we're really looking at ground source heat pumps and smart building design, and how we can actually use some of the generous resources that we have, or we're sitting on literally, to be able to save energy and through that decarbonize NZ, or partially decarbonize NZ, work towards that. I'll briefly introduce the two speakers today. Yale is the founder and managing director of Geo Exchange Australia, an honorary fellow of Wollongong University, and we'll I suggest Wollongong is still as pretty as it was when I was last there. Yeah, that's all good. Yeah. He's been working in sustainability for 25 years and actually working in geothermal for 15 years across the Pacific. So he certainly can hold his head up as an expert in this area, and somebody who's been working in New Zealand as well, in the Taupo area, looking at some district heating there. Anya's with GNS. Anya actually leads the geothermal activities at GNS, and is looking again at how we can use geothermal to try and reduce our emissions over the next, I was going to say 20 or 30 years, but we can do it a lot quicker than that, I think, in many cases. Just a little bit of housekeeping for us, please. If you have questions, and I'm sure there will be plenty, can you type them into the questions box? The way we like to run the questions is that at the end of the session, I will come to the questioner and open your microphone so that you can actually ask your question in person. We find that helps the engagement a bit rather than just people reading out questions. So I'll invite you to ask your question in person. If your question is for one of the panelists in particular, if you could indicate that, please, when you type in your question. And if for some reason you don't actually want to be made live on the webinar, then please mark that in the question as well, and I'll read out the question on your behalf. So I think that's enough housekeeping. We're starting off with Yale, who's going to do the first introductions. So Yale, over to you.
Okay, great. Thank you, Mike. Thanks all. I appreciate your time today. So yeah, my name's Yale Khan with a company called Geo Exchange. We've been sort of working in this space for quite a while now. Actually speaking with you today from the lands of the Bunjalung people, which is in northern New South Wales. I'm right on the edge of a volcano, but a little bit different to yourselves. This one went extinct about 28 million years ago. So just a little bit of difference between the geology that we have across the two countries, and how we, when we're looking at this concept of renewable thermal energy, everything's about looking at first principles and what's available locally. So just in terms of the images there, just to show a few of the examples that we look at, we've got everything from the hot geothermal stuff, which you're all very, very familiar with. We've got drilling into a closed loop for a closed loop borehole system, and we've got a lake in that instance, Lake Taupo, just to show the breadth of things that we look at when we use this concept of renewable thermal energy. Presentation here today is going to be mostly what was done in what was presented in Rotorua a couple of months ago. I've tweaked it a little bit to show a little bit more building examples, and then that'll flow in really neatly onto this work. So really quickly, we talked about the University of Wollongong. We've got a couple of really interesting research projects at the moment. That is the building on the top left, first living building challenge certified and living laboratory in Australia. They've got a geosystem in there. It's a net positive building, for lack of a word. It actually exports energy to other buildings on campus. Just to show you who else is using this concept of geo or renewable thermal energy around the world. Fresno Stadium in Beijing Olympics, had that done, had that 100 boreholes there. Top right is not recognisable as such, but that's the Microsoft campus in Seattle. They've got about 3,000 to 4,000 boreholes underneath the entire campus for all their heating and cooling. Not to be outdone, below them is Google, their new Googleplex, I think they call it, using about 3,000 energy piles to provide heating and cooling to that entire building. Buckingham Palace did a changeover many years ago, and I believe the Palace of Versailles is about to do one. And all those are using options of closed loop systems. One of the very originals here in Australia, at least, was the Opera House using Sydney Harbour. So all the air conditioning, everything from the Opera House actually uses Sydney Harbour through what we call an open loop system. So basically just pumping harbour water in through a heat exchanger and back out again. So what we go through today, I think particularly for everyone here and professionals here, everyone knows that we're not in a trend or anything at the moment around this energy transition. It is a proper transition. I'll just quickly go through that as some background. And then we'll look at this concept of thermal energy. We'll look at the context of sharing it, and then I'll look at some of the applications about, let's get us, is there a sweet spot? So I'll just quickly touch on that. And then quickly go through the Taupo East. We've got a couple of other case studies through the presentation. So trending or transition, we started this, or I say that we started this with the idea of energy star rating systems on our dishwashers and aircon units and kind of everything else. But it was really limited because we're only looking at the appliance scale. And then obviously it makes a lot of sense. Let's look at the building scale, and that came in things like Green Star, Living Building Challenge, all the various building rating systems out there. Parallel to that, we're making our energy supply more renewable. New Zealand's got a massive head start there compared to most nations around the world. I think already at around the 80% mark. And then it comes down to, well, we can supply it all renewably. And it's really, really cheap to do that these days compared to, a new solar plant at the moment is cheaper than running an existing coal plant in most countries. Then let's use it smarter. Let's look at the efficiency side of things, or even the energy productivity side of things. And the big thing that we're seeing at the moment here is not just about using less electricity to run our buildings, and I'll focus on buildings obviously for the purposes of today, but it's mostly also about getting rid of gas heating, because gas is now identified as, one of those big, particularly methane leaks and everything, identified as this really big sort of climate change issue and carbon emissions issue. So hence we've got these terms, decarbonisation and electrification, which really in most ways heat pumps, renewable thermal energy at the building scale, with the exception of cooking, of course, is where the solutions lie. We're digitalising everything at the moment. So Internet of Things, algorithms through AI, BMS sensors and everything else. That's a really big part of what we're seeing. And it's a really important part of how we manage the systems better. So we want to balance the combination of our variable energy supply with our variable energy demand for heating and cooling. And that, the algorithms and the thermal storage to do that is really the key to get that balance right between the two. And then we start to look at future designs, and things like resilience and adaptation are a really big part of that. The crater that I'm sitting on the edge of at the moment was, a lake only a few months ago with lots and lots of houses underwater. So the concept of resilience and adaptation is really, really close here, let alone our bushfires and everything else. So evolution of the two, electrical and thermal energy. I utilise this because I find that for a lot of people, most people are really familiar with the energy supply, the electrical energy, this industry, or how we get that. Thermal is a little bit harder, or not as obvious to a lot of people. So, but basically we both have a similar goals of reducing emissions, whether it's CO2 and methane, or global warming potential of refrigerants in the HVAC world, in the aircon world. But we're doing that now with lower demand because we've got more efficient appliances. Your dishwasher needs less energy now to do the same rinse, to do the same cycle it used to do. With better buildings, we need less heating or cooling on a square meterage basis. So we are reducing our demand on a unit basis. Storage and digitalization are becoming more and more important. I mentioned that before, that link between the supply and the demand side. Storage and digitalization will be the key to kind of link them together properly. And then it's all about our energy sources. Are they local? Are they renewable? The one area where we're not seeing this sort of parallel paths is in centralisation and decentralisation. So the most simple and obvious example for everyone in decentralizing electricity grid is rooftop solar panels. Everyone's got little mini solar power plants everywhere. On the thermal side, and it's mostly because we have a heating and cooling element, so we kind of got like a positive and a negative, if you like. We're seeing centralization often is becoming a much better approach to it, a more efficient approach to it, because we get this ability to basically just move thermal energy around as you need it from a hot side to a cool, from a heating demand to a cooling demand. So the renewable energy or the electrical energy people, everything used to be about combustion and gas wells and fracking and everything else. Now it's about, where you're sunny, where you're windy, where you have geothermal. We do that we can do that really, really well. In the HVAC world, we've typically still been stuck in let's just burn something and let's reject heat to the atmosphere. Or, and that's off a rooftop or a balcony or whatever it might be. So now we think about, okay, well, what else can we do? What else is available to us as these sources of thermal energy, particularly as it's obvious that we're just, everyone's moving away from burning gas. So thermal energy, we've got a whole bunch of different categories and where it can come from and sources and everything from the ambient air to solar thermal, the groundwater, biomass, buildings, the building foundations, and down the bottom, gas and electric resistance heat. The categories we've got there, they're renewable or they're non-renewable. So obviously we want to lead ourselves to the renewable phase, and they're either natural or anthropogenic. And typically on the natural, and both sides, I should say, of those, we obviously want to utilize that available thermal energy as sustainably as possible. And that's where it comes into the real design element of it. And so rather than having a table to look at it, we end up with a little bit more colourful, pretty picture here of looking at what are all these different sources of thermal energy around. We can see a subway in the bottom left. We've got storm and sewer on the bottom right. We've got a river or a water body through the middle. There's groundwater in there as well. We've got a data center feeding into an aquatic center. All these sorts of things, and we're just linking them together through basically a ring main that's joining all the buildings together. So sort of the start of the thinking that we want to get people moving to. And everyone, of course, in this instance, shows that some of them do have their own independent ground loop. The next category that I guess we use for renewable thermal energy is it direct energy, or is it direct thermal energy, or is it indirect thermal energy? So direct thermal energy is things like geothermally heated waters, might be high temperature wastewater from industry, or chilled water from the bottom of the lake, as is used in Toronto on the right hand side there. Typically we've got really high, really hot, really cold temperatures, and we use that directly. So we don't need a heat pump or anything else. We're just using that heat exactly as it is, often just with a heat exchanger to transfer the heat. Typically you've got only heating or only cooling. You can't normally get both out of it just because the temperatures are so high. When we look at indirect renewable energy, or renewable thermal energy, I should say, we're looking at typically temperatures are somewhere around a function of average ambient air temperature. And that could be the water body or it could be the ground. So, for example, the South Island, New Zealand will be around the sort of 10-degree mark, whereas up in Northland, you'll be in the closer to 20 degrees. It basically just moves as the average ambient air temperature increases. Now, because we're in that temperature range, we do need a heat pump in order to provide the heating and cooling needs into the building. But the good thing here is that because we're in a pretty moderate temperature range, we can do both heating and cooling, also because we've got that heat pump in there. And we can do that both seasonally and simultaneously. So it gives us a lot more flexibility to do that. And we're also able to provide thermal storage, and that's using things like the ground or water bodies as a form of thermal storage. And humans have obviously been using these temperatures for a very long time, whether it's all the way back to caveman or food, storing food. If you're a little bit more sophisticated, you might prefer to consider it as being the wine cellars in the south of France. When we talk about thermal storage in the ground, I said thermal storage is such a big part of this sort of usage, particularly with heat pumps. And that can be as simple as a hot water storage tank. There's phase change materials and other things. The example I'm going to show here is when we actually use the ground as a form of thermal storage. So our blue line here is our cooling needs through the year, or in the HVAC engineers or mechanical engineers will call it heater rejection. We're summer at the start of the year, so obviously that's highest, and as we come into the middle of the year, we can see the red line increase, which is of course heating or heat of extraction. So basically in the middle of summer, in the warmer months, we're ejecting heat from the building, taking heat out of the building, we're rejecting it into the ground instead of rejecting it, say, through a cooling tower or an outdoor unit of some description. We put all that heat in the ground, and then in the middle of winter, we're basically pulling that heat back out again. And then, of course, a few months later, it goes back into the ground again. So it's what we call annual or seasonal storage using the ground. And of course, we can also do that through very short-term periods. So it might be heating a building in the morning, cooling in the afternoon, and then maybe heating at night again if there was a meeting or something happening in an office space. So we've got this ability to basically take heat or thermal energy from the building into the ground and back up again, pretty much as we need, just by circulating water around. The other concept that we see more and more of is one called thermal sharing. And this can be present at all different scales. And so at the individual dwelling scale, the example I'm using here is just that you heat your pool with the heat rejected from the air conditioning system. It may also be that you just heat your hot water from the heat rejected from the air conditioning system. There's already systems out there, heat pumps out there can do that using a superheater. In commercial offices, it could be that with simultaneous heating and cooling across different zones. So, whereas once upon a time, and so often, you have a boiler on this side of the building and a chiller with cooling tower on this side of the building, they're basically fighting each other at various times. What we want to do, and VRF systems and others already do it, is we just move thermal energy around the building to heat and cool as we need. In between buildings, our favourite example is always a data centre heats the local swimming pool. And we've actually got, it's coming out of Norway, Celia, for those who know her, has just had a meeting over there. And in Norway at the moment, data centres are required to get rid of their heat into some sort of local heating system. They can't just, sort of let it go into the air through a cooling tower. And we've got one of the PhD students we're supervising at the moment is actually linked through Norway University, through NUT over there, and this is exactly what they're looking at the moment. And then we go, rather than just having building A to building B, now we're at the district scale. It's like, so the original district heating systems, and they were called district heating systems, and you think of the steam in New York City or in Manhattan there, places like Copenhagen and various Boise, Idaho has had a geothermal system since the late 1800s. Some of these systems have been around 130 years or so, even going back to the Roman times, where they basically would have local heat, either waste from a power plant or something, or geothermal heat, and they would just pump that around to different buildings for a direct system. Often they're called sort of first to third generations, where they're using variations of just centralised, hot and cold basically to heat or cool buildings. What we're seeing a lot more now is this concept of a low temperature exchange, and they're calling these fourth and fifth generations, but I find they're pretty messy definitions of them. But basically what they are is that we've now got a ring main, which is basically joining buildings, which is at low temperature and ambient style temperature, so somewhere around, let's call it 15 to 25 degrees. Every building has its own heat pump, and all those buildings are feeding into this ring main, and then there's different sources of thermal energy that are sort of maintaining those temperatures. I think the next picture. So when we've got a centralized system, you can see here you've either got a typically 2-pipe or 4-pipe system, hot and cold. You're generating your heat or your cold centrally, pumping that around all the different buildings. One on the top left I've shown there is Ball State University in Indiana, which pulled out a couple of coal boilers and then put in a couple of thousand boreholes under their sporting fields and pumping hot and cold water around their entire campus. They've gone for that 4-pipe approach because they had such an array of all different buildings everywhere. Whereas I think there's an argument now probably a lower temperature approach could have been really useful, different heat pumps in different buildings to match the requirements of each of those different buildings. So it's a bit of an older system. So when we talk about this is a 5th generation system, so we've got this low temperature network, which is basically joining all these different buildings, homes, whatever it might be. They all have their own heat pump. So it means that the heat pump can suit the building needs, whether that's to heat a pool, to do underfloor heating, to do centralized aircon, whatever it may be. But everyone's feeding into this system, and we've got this ability to control this system, and everyone just utilize it as they need it. Much better ability to look at partial loads and everything else here, and you've got a lot, almost a simpler system going around with everyone connecting in. So just have a quick look at applications and case studies. So I raised a question before, is there a sweet spot? Um, it depends, and I use that a lot when I answer questions. It depends. It all depends on this, this sort of four sectional Venn diagram I put together there. It depends on how much you run your system. Does it have a mix of heating and cooling? What's your local climate? Does it have the extremes? Does it need a mix of heating and cooling? What are your finance costs? Everything from your running costs like electricity and gas through to the cost of the actual heat exchanger itself, your connection in with your source of thermal energy. And then it comes down to things like your building owner and your building costs. It could be the business model that people have. So we find there's a lot of options here. And I've got a note there for carbon credits as well, in terms of how that feeds into the system. And then beyond that, and then we've got things like the actual building design itself. Is there a location to put the ground heat exchanger, sorry, the GHX ground heat exchanger? And do we have other benefits? So what we find with a lot of systems is that when you get rid of rooftop equipment, the need for gas boilers with ventilation, the need for air source heat pumps that need ventilation and big spaces as well, you often end up with a lot of other cost savings on the building itself. It could be less structural requirements on the roof because now you don't have all this heavy plant equipment on your roof. And you might actually use that roof for something. So it could be more solar panels on the roof. It could be a entertaining area of some description. So it frees up a lot of space and gives the architects a lot more flexibility in what it is that they're doing. So is there a sweet spot? Yes. Is it always the same on every application? No. And why? And just quickly the reasons and various excuses. Sometimes you just can't get a ground heat exchanger connected into a building, whether it's groundwater or whatever. Just because you don't have the space doesn't mean you can't do it, but there's just, sometimes there's your practical limitations to it. One of the biggest barriers that we often find is just this client perception. And that client perception can sometimes be the project team, the engineers, etc. as well. We've got a project at the moment in Canberra, which is a significant project, a real benefit to the client. Mechanical engineers said, the ground temperature is 17 to 18 degrees, which is not hot enough to heat the building, so therefore it won't work. Obviously not at all understanding how a heat pump works and not recognising the fact that their air source equipment is expecting that to work on a -5 morning, but the ground won't at 17 degrees. So we get these weird perceptions of stuff around technology risk and a poor understanding of it, which is, often the biggest barrier to uptake. Business case, obviously always important. It's just about understanding capital costs of the system, life cycle costings, how is the client looking at their business case and their life cycle costings. We often say in this area, some of the financial tools are as useful as the engineering tools to make this happen. And that's the case for a lot of the green technology or the energy transition that we're looking at. We need to be looking at things a little bit differently and not necessarily we're trying to change the way we do things from an engineering perspective. We need other elements of a project to also come to the table in that respect. Look, and sometimes you just don't use the building often enough. With holiday homes or, sometimes certain schools or a certain building in a school, which is like the remote classroom hardly ever used. Maybe you don't hook that up onto the system, but you might do the rest of the school. And then has it really been considered, everything from base load systems to hybrids, and has it been considered by someone who fully understands the technology and the connection, I guess, between the geology, the geography, the, whatever it is, the geothermal elements, but also the building side as well. There's no point saying, we've got all this amazing groundwater, all this amazing whatever for a system, but then no one's looked at the buildings and whether or not they, we kind of integrate the building really well. So lots of sweet spots. Top left, Geoscience Australia in Canberra, closed loop borehole system. I'll run through these pretty quick just to show the variety. Ski lodges in Hakuba in Japan for the skiers amongst you, using basically snow melt to heat the ski lodges. A data centre in northwest Australia with 28-degree ground temp, which is kind of worst case scenario possible. An aquatic centre, which is both what I say geothermal and geo exchange. So 35-degree groundwater to heat the pool directly, so in direct thermal energy. And then after we've done that, that water then goes via some heat pumps. And by using those heat pumps, we provide space conditioning to the space, and then heating and cooling to the gymnasium, to the foyer, to the admin, to the offices, etc., etc. So a combination of things there. Groundwater on the bottom left to an art gallery. Still, so I've got to get a picture of art galleries. Art galleries and museums, the reason I show that is that all we're doing different with this concept of renewable thermal energy is where we get our energy from. distribution through the building is the same as everything else. So if you need really tight humidity and temperature controls, you can still do that. That's a mechanical engineering question. It's not a thermal energy question of where it comes from. Down in Hobart, using the Derwent directly, so looking at similar climate, temperatures, etc., to New Zealand. That's a ferry terminal for Mona, which is one of the sort of really famous galleries and museums here. Sorry, and we're just using the river water basically to provide heating and cooling through that building. And I've just got a picture of a house there. Suburban house. We do everything from inner city suburban to rural residential sort of homes, all different types of ground loads. Let's go through Taupo East. I've trimmed this a little bit just so we can move through it. What we've got here is about just over 2,000 dwellings. And really what we're showing here is just square meterage in kilowatts of each, and a diversified total of about 20 megawatts in total is what we're looking at for this project. If we looked at all of those dwellings and a small commercial area. The process that we go through, and I've used this example in this case to show the process we're going through from this thermal energy perspective. We need understanding the building requirements is every bit as important as understanding your source of thermal energy. This, the whole approach here is integrating the two and making sure they work together, and obviously you have a longer term sustainable system. So on the feasibility, we analysed everything from the single dwelling level, which we just nominated as being a 12 kilowatt as an average dwelling. For some dwellings that might be all of their heating and cooling needs, for others it might just be some zone. It just obviously depends on the build quality and the size of the dwelling. We also looked at the precinct and development level. Where we've done an analysis on the single dwelling, we're talking about that sort of at the homeowner and what that means. And the precinct analysis is talking about obviously the larger scale. And we also looked at things like centralised and decentralised systems. And what we ended up considering here was utilising these systems with every building, mostly residences, having their own heat pump. That way, again, they can decide if they want a underfloor heating system, if they want to heat their pool, if they just want a standard sort of split aircon style approach, they can do whatever it is that best suits their building. So further considered through the report, ambient air. We haven't considered ambient air, but it's never discounted in anything that we do because it's obviously such a ubiquitous supply of thermal energy. We looked at closed loop and open loops using the lake. We looked at deep closed loop boreholes, so approximately 100 meters deep. We looked at shallow closed loop boreholes, so about 50 meters. We looked at shallow groundwater, approximately 50 meters deep again. And then things like additional sources and a hybrid, which is where we combine systems, is, they're all pending sort of further consideration. Now, the reason we didn't go deep and didn't go to the closed loop systems. Closed loop borehole systems typically will be a lot more expensive to install. So your business model payback doesn't typically work as well. And that's particularly we find more so in New Zealand compared to say over here where we see more closed loop systems. But that's because of our geology and we're a really, really dry continent. One of the things we're also very careful of here is there was sort of, at the time, there's a bit of uncertainty around it. So let's just say the geothermal zone itself, the deeper geothermal zone is off limits. That way we don't want to go too deep and, potentially cause some issues in there. If that changes at some point, then, that can be, the advice becomes different. That can be considered differently. The other thing is that if we do go into the deep geothermal zone, then we potentially lose our ability to do cooling. So from the system. So that's where we need to sort of be cautious, if you like, on, even in this instance, what depths we go to. And I'll just check that. I'll go back up. The other thing that we've got here, you can see the geothermal zone runs across the development site, just in the slight red there. Temperatures towards the northern end of the site, we're expecting to be around the 40 to 50 degrees in that shallow groundwater, but around the 20 degrees in the south. So we've got what we call geothermally influenced versus geothermal water as such. And so we just, we need to be just aware of that in terms of operation of the system. So the reason we have that for the geology people out there, basically what we've got is we've got the surface, and the top 150 meters, we've got this Ruanui formation, which is all the pumice, etc. And all the groundwater in the 10 to 30 meters or so is basically just rainwater, just rainfall that just falls and creates groundwater. What we find is that you've got this sandstone and cap rock, mud rock there, mudstone cap rock there. But the deeper formation is where the high temperature geothermal is. And there's fractures in that middle zone, which is why we've got this sort of geothermal influence of sort of warming that shallower groundwater section. We also looked at the lake. So we looked at groundwater there. We looked at and all the other geology options. We looked at the lake as well. A couple of distance to the lake and possibly some regulatory questions still around use of the lake. So that's something that's to be considered. And we looked at the water being both an open and closed loop system. So open loop system, I mentioned Lake Ontario before. For Toronto, basically pumping water straight in through some heat exchangers back out. Or we could do a closed loop system, which is a system in which, similar to what we've just done in Sydney Harbour the last sort of year or so, where we've got a closed loop heat exchanger in Sydney Harbour itself. And then the shallow groundwater option on the bottom right is just where we basically pump water up through a heat exchanger, put it back in the ground again. And while we're showing that system there on a single dwelling, we'd have them on a sort of communal basis, if you like. There'd be multiple buildings connected up to each individual ground water bore. So in terms of efficiencies, how we then look at everything, we've taken some really sort of simple approach here, but entering water temperature is the water that comes out of the lake or out of the water body up into the heat pump, and then the heat pump, and we're assuming here the heat pumps are all delivering the same thing into the building, which is obviously a fair assumption. And that's the coefficient of performance, so which is basically the percentage of, so kilowatts in for of energy, electricity in for kilowatts out. As you can see here, the closed loop in the lake, that has a lowest entering water temperature because we end up sort of circulating water through the system. So it's got to be lower than the 12-degree lake temp. So it's got our worst COP. We've got an assumption that the lake temperature at 12 degrees for an average, so that gives us a slightly higher COP there. Purely, again, we're starting with a higher temperature, we're in heating mode. And then if we use the groundwater and we just use our 20-degree number there for the south, then we get a COP of 5. So you can see that increase in entering water temperature into the system does give us high performance. That, of course, makes a lot of sense. So when we look at the energy analysis for everything, we've got it on the different elements of it. The main thing here is just on the savings, and arguably just the very bottom of the savings in the darker column. So we've got it for the lake closed loop, lake open loop, and the groundwater open loop. And you can see there we get percentage savings ranging from about 38%. And because we prorated this development, all the percentages are, are basically the same. 38% from the closed loop for the lake, up to 43%, up to 47% for annual energy savings on the, through those different scenarios. So we're looking at call it 40 to 50% energy savings. On the peaks, which is that electricity demand during that peak heating period when when temperatures are at their absolute lowest, this is compared to air source equipment. So using the lake, we end up with about 35%, up to 44% on that open loop. Now, where the peaks become really important is on a development wide, what they mean is it might have an influence on the amount of electrical infrastructure you have to bring into that site. So so if we're reducing that by 40%, that might be a slightly downgrade of a transformer or a substation or something. We've got a project at the moment which is saving about $5 million. They don't need to do an electrical upgrade. So there's some significant savings that can come from the minimising or eliminating the need for electrical upgrades. And that can happen at the house scale, but also obviously when you do this at the larger scale, it has a much bigger influence. From the financial, I've just got here the dwelling and the development. I've cut out the middle section on the precinct. Very bottom row again is probably the more useful one. A groundwater open loop was a lower cost to install and more efficient, so it has the best simple payback. That obviously just makes a lot of sense. Down around the 3-year mark, up to 8 or 9 years if we go with a closed lake loop. And this is just the energy savings on the system. As that system's operated, it gets operated as some sort of thermal utility arrangement, then there'll be, the operations and everything of that have to come into play on those. But you're starting at obviously a very good base in terms of understanding the payback scenarios on the system. So that's the energy and analysis, etc. So in terms of the non-technical, these are obviously really important. These are also as equally as important, and often often the limiting elements, if you like, to a lot of things. So things like regulatory access to the water, environmental approvals, utility connections, all got to be considered, all got to be done properly for all the consents and approvals. Some really interesting conversations globally at the moment around consenting and approvals for, say, a solar farm or a wind farm or whatever. And yeah, of course, it has to be done as well as anything else, just to make sure things are done properly. Social approval, do people understand it as an education element? Will they connect to it, basically, is what it comes down to. You're putting the system in, you need people to connect to it. You might want to offer incentives for them to connect to it. And basically, do you provide a proposition that's just too good to refuse? Like, it just makes sense to connect into that system and not to go off with something else. And then the ownership models. So that's ultimately where it all comes down to. Whether it's private or public, how you have a performance agreement so that, you're obviously guaranteeing performance to like a service agreement, like anything else. Metering and sensors and stuff is really simple these days. And then things like billing systems and service. So really, look, you're just talking about a utility. Just said now, think of it as a water utility. So that water is being used for heating and cooling instead of to, flush the toilet or wash your teeth or whatever. So next steps on any such project is, is that stakeholder consultation, all your consent and approvals, understanding your ownership models, update the building loads. As I said before, the building loads are as important, understanding them really well is as important as understanding your groundwater conditions, your lake conditions, whatever it might be. Do some field investigations to model and verify everything that's there, and then you finalise the system design on the basis of all that data. That was it. Thank you. I feel as if I rushed a bit. Apologies if that was the case. My details there. Hugh Williams, who some of you know, he's in New Zealand for quite a while. He's actually back over in Europe at the moment. We work together on Taupo. We work together on a number of projects. So please feel free to reach out. I'll leave it to you, Anya.
Wow, if you don't mind me saying, how much information was that? For everybody's extra information, we are recording the session, of course. So if you want to have another look at some of that, then by all means have a look at the recording. That should be up and available on our web channel probably later tomorrow. But I've taken enough time there. So Anya, I am just going to make you the presenter. So we should be able to see your screen now, if you'd like to put that up. And you are muted as well at the moment. And we've got your screen. Perfect. Away you go.
Me on the screen?
Yeah.
All right. So I chose to go after Yale because he did all the technical and the detailed stuff, and I'm just really doing a pretty demonstration of a handful of systems out of we've probably got near 200 systems set up in New Zealand. So yeah, I'm just going to present a handful of those to show you that we can use these systems here in New Zealand quite readily and easily. So again, my presentation is 90% what I gave at the SEEP conference, but just taken out some of those introductions that Yale has already covered. So I'll just start off with all the opportunities there are in New Zealand at the moment to be considering these new efficient, well, they're not new, but these efficient heating and cooling systems. This is just some highlights from the 2022 emissions reduction plan that was released late May, and all in blue are sort of areas that heat pumps, beautiful solution. So to improve energy efficiency of our buildings, reduce our reliance on fossil fuels, replace low to medium temperature boilers, warmer, drier homes, sustainable and affordable energy security. So reducing our demand on the electricity grid by reducing, taking away that demand on our electricity grid by having this high COP heat and cooling source, improving energy efficiency of our buildings and accelerating the shift to low carbon practices. So geothermal in New Zealand, one big drawback is that we automatically think, I say drawback, I'm a geothermal researcher, I shouldn't say that, but is that we automatically think high temperature geothermal. And the systems we are looking at are those systems off to the outside of those geothermal, hydrothermal systems where the high heat is into those ambient temperatures outside of the system. These ambient conditions are generally just ground heated from the core. We've got a core heating up our earth, but also subsidized with solar heating that is stored in our soils, rocks, and water bodies. That map on the side is just showing our temperature variations in the top 1 meter of our soils and rocks in New Zealand. So as Yael said, 16 to 18 up north, coming down to 10, some quite cold ones in the areas that we don't really live. How our ground temperatures propagate, we do have seasonal variations in the shallow, but as you get deeper, those and I guess the range of your temperatures sort of equilibrate out to roughly your mid ambient air temperatures for the region. Sorry, go. Ground loop systems, as Yael alluded to, we utilize the ground heat. There's a series of different formations depending on your building needs and your land access. So here's just a few shallow horizontal loops. You obviously need quite a big footprint of land for your building. Basically, your ground loops are designed towards your building needs, and it sort of maps out as a length of surface area, so meterage. And so that's why you get these ground loops looping back and forth to try and increase your meterage, so to meet your heating needs. So the one in the middle is showing a slinky ring, which is basically condensing your footprint by overlapping your coils into a smaller area. For higher building needs or smaller land footprints, you often need to drill vertically down. Again, there's the water system, so accessing those surface waters or the subsurface water systems where you've got these open and closed loop type systems. Both of these illustrations down to the aquifer here are actually open loop. The one in the middle is where you take your water up, operate it through your heat pump system, take the energy you need out of it, and discharge it to a soak pit or back down into your aquifer. And then these surface water systems are basically an exchange system, much like those closed loop ground dry systems. So yeah, I'll just run through a few examples, just of a handful from around New Zealand that are utilising ground source heat pumps. This is a single dwelling in the Kapiti Coast region, so just north of Wellington. They obviously have a bit of land, so they dug up some coils, dug up some land, put some coils in, and they wanted it primarily to reduce their energy costs and allow them to have a pool. So in doing so, they heat their whole house of about 400 square meters and their pool for pretty much the same price they had for just a smaller house that they had on the site beforehand. This is one in Canterbury using a single open loop. Again, this is a large house, it's about 300 square meters. Again, taking water from the aquifer systems and pumping it back down. No, they're not, they're just putting it into that sinkhole there, that beautiful water feature in their lawn. And again, their highest thing was the energy savings and also reducing the diesel burner, which is what they were operating before. Wairakei Golf Course, just out here outside of my windows, is the Wairakei Golf Course. We're in a high temperature area, but we're just going to utilize, well, they're utilizing their water features. So these are hazards in their golf course. They have these ponds, so they put a heat exchanger in, which you can't quite see in that little picture there. They're well hidden in their water feature, and they're using that to heat and cool their club rooms. Christchurch Airport, on a much larger scale, using free groundwater for cooling of their warehouses and their buildings. They also have a whole pile of other initiatives going on to reduce their carbon footprint. But this was, I think, step one was getting their energy efficient heating systems operational. So that's been going for many, many years. I think pre even the awards, so late 2000s. This is a Lower Hutt Council building, obviously based in Lower Hutt, and they had to actually strengthen their building for earthquake security. And in doing so, the architect put down 70 piles down to 20 meters, and they just line those with pipes to get to allow fluid to rotate through those pipes into the groundwater, where they extract cool or heat, and then it's rejected into the flow and ultimately out to the sea. Just recap some of the benefits and barriers. Ground source heat pumps, obviously renewable, sustainable, freely available, low operating costs, highly efficient and long lifespans, and quite aesthetically pleasing, which, there's nothing outside your house. There's no solar panels, there's no wind, there's no air flow. It's under the ground, it's not there. And barriers, as Yael alluded to, the biggest one we see in New Zealand is still people's mindset, lack of awareness. The upfront costs and considerations is quite as Yael walked us through, quite a lot of initial feasibility and then more detail, and you really need to know what you're building for or what your building needs are, and then you can design those systems based on your geology and your local resources. There's also regulations around them, potentially. It depends on which district you're in and where, and zoning or whatever, that you have to talk to your councils around that. And I guess also the ease of other renewables, as Yael said, it's quite easy to go out and grab a solar panel, realize you're not producing enough electricity, go out buy another one. And same with heat pump systems, air-to-air heat pump systems. So what can we do to overcome these barriers? I mean, as Yael also showed, it's not new, raise awareness, learn from overseas. What can we do here? Like, how do we reduce those upfront costs? And what can we really learn from overseas? And how can we apply them here? So just the next few slides are just recap and present a handful of things from overseas that I think would be really, really key areas that we can work on or push in New Zealand. One is the use of our seawater. We've got such a large coast, and most of our population is sitting on our coastlines, and it's quite easy to put one of these heat exchangers down, as Yael said. This is the example of Sydney, that's providing heat and cool for apartment blocks and commercial areas. Other one is think bigger, much like that Taupo East case study. We get more cost benefit from thinking larger, getting more people involved, cutting down those upfront costs. This is an example from Zurich in Switzerland, where they've got a whole district that's operating and extracting and dumping heat to a subsurface system for a whole suburb that involves, I guess, accommodation, apartments, office blocks, sporting facilities, and they just pull heat or cool from the earth and dump it back down when they don't need it. Again, this is a good example here. This ice skating rink also partnered with pools, quite a common thing in North America and Europe to do, so you can exchange heat from within your buildings and your facilities as well, and not necessarily having to dump and extract from the ground. So just really smart energy use. Greenhouses, covered crops. Currently in New Zealand, they mostly operate on gas, and they have a big push to transfer our veggies and greenhouse facilities to greener sources of energy. This example from the Netherlands, they actually drill down quite deep to get 80 degrees water. If you put a heat pump system onto that, we can probably operate these from a lower, shallower depth. And then finally, schools. I think this is a big area that we should be seeing some progress in. We have a big transition of schools and government buildings from fossil fuels to renewable energy. Ground source heat pumps are ideal. Most schools have a playground or a sports field. Utilize that for shallow ambient ground temperatures. This example in Texas, it's quite a large school. They put in a whole renewable energy system. So they've got geothermal, solar and wind. And in their lobby, they've got a information wall that basically monitors and shows you where their electricity and their heat is coming from at any given point in the day. So the kids can see and understand the balance of heating and cooling demands and different perks of different renewability. So also educate the students, they educate the parents, they educate the community, and then we can hopefully transition to low emissions energy much quicker. So yeah, this is where I see the biggest opportunities in New Zealand is smart city planning, looking at district heating, co-location of industry and commercial residential, and use of pre-existing infrastructure, subsurface infrastructure. Again, benefits for heating and cooling of remote communities, less dependency on our electricity grid potentially, and yeah, fossil-free public buildings, council buildings, school buildings, government buildings. This is a great opportunity for this low temperature geothermal to be considered. So our takeaway messages, I'm putting our names here because I've got Yale's on here as well, is smart use of Earth's natural heat resources can reduce our demand on electricity and reduce our fossil fuel usage. Ground source heat pumps have the perk of being available for both heating and cooling at virtually any location. And we've got proven examples operating globally and here in New Zealand. So if you want any more information, please reach out to Yale or myself, or ask on the chat. Cheers.
Thank you very much, Anya. That was excellent. Highly informative stuff. A few questions already coming in. So first of all, if we could go please to John, you're the first question. I'm going to unmute you at our control end. You may still be self-muted. And if you click off your share screen, what I'll do, I think, is shall I take back control of that?
Yes, thank you.
And I'll take control of that. That's all good. Yeah, I'm coming to you, John. You're muted at your end. So if you'd like to unmute, you can ask your question. And I see you've got your hand up. What I'm going to do, John, I'm going to try and work that through. Erin also has a question. So, oh yeah, you're coming through.
Okay, thanks. Yeah, my question is, can you use ground source heat pumps to heat water up to higher temperatures around about the 92, 93 degree mark to use for sterilisation?
Yeah,
you're on mute.
Yeah. You're on mute, yeah.
Let's try that again. It is a function of the heat pump and the refrigerants involved with that heat pump, more so than necessarily the geo concept itself. There's a lot of new heat pumps coming to the market now. I've even seen some coming out of Europe in the 150, 160 degree sort of temperature range. So there's a couple of ways to approach it. One is to look at these newer heat pumps with these, these different refrigerants. CO2, for example, will get you up to that at least the 70, 80 mark. And you can either look to do it in a full, do the whole step yourself, or with the system, or do it in a stage, almost like a preheating approach. There's sort of two ways that people are looking at it at the moment. But I'd say it's a bit of a watch this space in terms of the new heat pumps coming onto the market.
No, thanks, John.
Thanks, John. Erin, just coming to you. Oh, I can find you on the list. There you go. You're unmuted at my end, and I can see you live. Question, please.
Oh, yeah, thank you. Good afternoon. I've got a question relating to, I guess, potential problems of fouling of pipes and or heat exchangers. This may happen in areas where there's hard water, so you just naturally get calcium buildup in the heat exchangers or piping. Then a second example might be making use of industrial effluent waste streams, which can have quite a range of different contaminants. And if you've come across this or these sorts of challenges, how do you prevent or keep the heat exchangers and pipes clean those situations.
For me to take that one? Yep. That is a sort of ongoing question. One of the first things we always do with such systems, and it's everything from salt water to sewer heat recovery, etc., is your selection of your pipe materials is of course important, just even from basic corrosion or whatnot. But then you've also got obviously your fouling. So then it comes down to maintenance of the system. We always have a secondary heat exchanger on these systems, so we're not running that water into the heat pumps, running it through we're separating them off, and then it comes down to how you maintain that. And of course, that really will be a function of what the issue is. We've seen some with salt water where they just do a basic freshwater flush regularly, and that kind of is enough to keep mollusks out or to make it okay. I've seen some people do acid washes and all sorts of other things. So it really comes down to doing what is required and appropriate for the application.
Okay, does that answer your question, Aaron?
Yep, thank you.
Thanks, Aaron. And I think it's good news. We actually don't have any more questions that have come in anyway. I'm sure both presenters would be delighted to take questions offline should they come in later. I see some nods. So it falls to me to say, and we're finishing on time, which is always a good sign as well. So thanks to you both for your time today. Fascinating presentations, as I think the conference does. The feedback from the conference was that they were fascinating presentations, which is why we invited you. It gives me the opportunity to plug our 2023 conference, of course. So anybody who is on the, we've got another question coming in actually, so I'll flick back to that in a minute. Anybody wants to see top quality sessions like this over 2 days, come to Wellington next June. We do have one, so I'm going to switch on the microphone for Andrew. So Andrew, you're unmuted at our end. I can see you're live. Your question, please.
Yeah, hi. Firstly, a great presentation. Thanks for that. Question I've got is, I've got a couple of projects looking at ground source, and wanted to know where do you start in terms of finding out the geothermal properties of the soil of the ground under your site? Is it a desktop study, or is it best thing to do is a borehole and then do some samples and find out what you've got?
Yeah, look, really good question. The typical approach we take on things is just desktop study to begin with, understand your sources of thermal energy, whether it's geology, water, whatever it might be, and then understand your building requirements. Normally at a desktop level, you can get a feel for, or you can make an assessment as to what's worth progressing with, and then you can if you need to go and drill holes and do your field proofing and your field testing, go and do that afterwards. It's, there's a big cost difference between the two stages. So we find that for 99% of the clients, it's about do the desktop first, and then if the results are good, then obviously go and drill holes or do whatever else you need to do.
And is that a geotech engineer you talk to, or is it someone else? Who's the expert that gives you that advice?
The expert is someone who can combine the two or get an understanding of the two. It's obviously something that we do, but what you need is someone who can get a good look at someone who can bring the two together. It might be, it's going to depend, and I find it's an awkward one to answer because you'll have some geotech people who'll do it really well. You might have a groundwater person who will understand it really well, but it's sort of the field or the discipline, if you like, which starts to, I look at geosystems as being a combination of about 5 or 6 different skill sets. So sometimes you need a little bit of all of those people to bring it together, make it work, which is kind of the frustrating part of it as well. So yeah, you're looking at sort of geology, ground-based people at the moment, and it'll come down to the individuals involved, basically. Just because they've got a certain badge or qualification doesn't necessarily mean they'll be able to sort of marry it together, if you like, in terms of looking at the thermal component of what's in the ground.
Okay, all right.
I was just going to add that we at GNS do have quite a bit of research work done on our groundwater systems and our local and regional geology. So feel free to contact us and we can see what we can pull out rather quickly for a desktop as well. Yeah, and we're also trying to pull it all together so we've got a usable online map that might give us a bit of more information or easy access of where we can get that data. Yeah.
Okay, cool. Thank you both.
Thank you, Andrew. We've got another question from Jonathan. So Jonathan, you're muted at your end. If you'd like to unmute, please, you'll be able to ask your question.
G'day, my name is Jono. I was just wondering if you've had any progress or discussions with getting any government level incentives for larger scale ground source systems in New Zealand. Has anyone made any of those discussions yet?
Yeah, I think we probably both. There's definitely some interest coming in through from the various government agencies. It's definitely a technology or a concept that they're got an understanding of and are very interested in seeing being developed further. Obviously, I can't speak on their behalf much more than that. And obviously, Anya come from GNS can respond further.
Yeah, I was just going to add that there are a few. Oh, there it is. It's still there. There are a few government feasibility funds available if you're decarbonising a business or decarbonising an entity. Have a look. I would say either MB or ICA would be your places to have a look, or even Ariaki, which is the transition CRI. And they've got some funds, but yeah, you need to figure out your use and your needs and where it slots into all that government jargon to find out the right funds. But again, we can help. If you want to reach out, I can try and point you in those directions offline.
Thank you very much.
Okay, thank you, Jonathan. So yeah, we're just after 2 o'clock. Thanks again, Yael and Anya, for your time today. Thanks to the audience for some really interesting questions there on the back of your attention and attentiveness for the last hour or so. So thank you all, and hopefully we'll see you all soon. Kia ora.
Thank you.